Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
Go above and beyond.
they become very good at what they do, but only
0.1%.
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
With Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. I have a returning guest that's becoming one of my favorites. His name is Joe Bhakdi. He's the head of a company called Quantgene, Quant Gene. We talked about cancer and the new therapies they're working on to help with liquid biopsies to identify cancer faster and better and more completely. They're also in the COVID testing arena. And this is important because, again, Quantgene and Joe, they seem to have, they approach problems in a really unique way that they get them solved, I think, in a better way. So I want to talk to them about COVID testing. So Joe, welcome back. Thanks. How you doing?
Hi, Richard. I'm great. Thanks a lot for having me on.
Well, good. So why, it seems like, a lot of companies and initiatives are researching COVID, trying to do testing for COVID, et cetera. Why did you throw your hat in the ring and decide to do it too?
So at Quantgene, we are all about what we call real-time medical intelligence. And the idea behind that is medicine is mostly a data problem. If you knew everything, there wouldn't be any problems, especially if you knew things before they become a problem. That's how we started in cancer. We became very strong there on the AI and data side, but also on generating this data with molecular diagnostics. And in COVID, what we saw is that there is, in a weird way, it was a similar problem. It was about real-time medical intelligence. The entire testing crisis in COVID is basically a real-time intelligence problem. You're testing, but the results come in too late. And in a pandemic, in an infectious disease, in a viral disease, time is of the essence because viruses, they replicate exponentially within your body, but also a pandemic spreads exponentially when it's not being intercepted. And so if you take a step back and think about COVID, what is the actual problem here? The problem is that you have to intercept that spread inside your body through medication and doing certain things, but also within a population. And the only way to do that is early detection. So it's literally right down our alley, what we do in cancer. We lead the world in early detection technologies in cancer. And the way we achieved that in cancer was mostly, there's a lot of chemistry involved and a lot of sequencing tech, but it was mostly through cloud systems, right? Software, AI, but also just good old cloud systems that connect large data sets and make them all work. And so when we saw the COVID problem, what we realized is it is not a molecular diagnostics problem. We have PCR tests in COVID that are nearly 100% accurate, 99.999% actually, the Attila and some others. The problem was that people don't get their test results back in time. So you probably saw all these scandals about LabCorp and Quest. They totally failed. Quest just got fired by Florida government because they didn't get 75,000 results back from, I think, May or something. so people got tested in May and they still didn't get their results back. I'm not sure.
Well, I heard it wasn't just the timing, but it seemed like the tests themselves, depending on which kind, was 2 to 29% inaccurate. So
that's on top of everything. Exactly. So, and that's not a problem of the test. That's a problem of the test handling of lab directors not having oversight. They are basically completely overwhelmed by this whole thing. And so what we saw is just a dire need in America for real-time, rapid PCR-based testing. And because of these delays, right, we now see all these phony initiatives from Abbott and some other companies that start doing these antigen and also antibody tests, which don't make any sense, right? These tests are bad. They have a terrible sensitivity. They have false positives. So if you use tests that are just not reliable, that is not something that works. And
well, let's get into some of the science first. what is sensitivity versus specificity? And then I want to ask you about PCR itself, how it works.
Yeah, so you have basically three different types of tests. You have antibody tests, you have antigen tests, and you have PCR tests, just to start there. The antibody tests, they check your immune system reaction to the virus or to whatever, but something that might look like the virus. So it basically investigates if you had COVID in the past, and if you have antibodies built against that virus, which would indicate that you had it. That doesn't tell you if you have it right now because there's a delayed immune reaction. So it's a bad test to check if you actually have it. It's a good test to tell you if you might have had it in the past. The antigen test tests for the molecules, for the proteins that actually are used by the immune system to build the antibodies. And so these are proteins expressed by cells on the surface that are infected by the virus. So it tests directly for the virus, but not on a genomic basis, but on a protein basis. And the problem with that is you cannot amplify proteins. So you can only look at what is actually in the sample. You know, if you have 1,000 viruses in the 1,000 virus proteins in the sample, that's all you can see, which you cannot see.
You're also looking at, I guess you have to do blood. If the virus, for instance, targets alveolar cells, epithelial cells, you're not going to use that as your sample. You couldn't even get to it probably, and then
exactly.
Okay, makes sense.
Exactly. You. I mean, then the next question is, how do you even get? What do you take? What kind of sample do you take? And exactly, you could have it in the blood, but then you take a nose swab, and maybe you don't find it there. It's not enough in there. And then finally, you have PCR tests, which are by far the most accurate. They test for the virus RNA, for the genomic material. And the big advantage why they are so accurate is that in a PCR reaction, you can amplify the RNA. And you can amplify it by billions of times, like 2 billion times. So if you have one molecule in there, you will amplify it to 2 billion, and then it makes it very visible. That is why PCR is literally like billions of times, more accurate in terms of picking up individual molecules. Now, the problem with PCR tests is they require a little bit more involvement because you have to run PCR machines, and so you need laboratory technicians. So in other words, you need a lab to do it, whereas an antigen test you can put on a little stripe and do it in 5 minutes on the spot. But that, of course, also leads to the point where you have, a bad sensitivity. To your question, in diagnostics, you always have these two important metrics. One is sensitivity and one is specificity. Sensitivity means if you have 100 COVID patients, well, it can mean different things, but let's start. Clinical sensitivity means if you have 100 patients with COVID infected and you do the test, how many of these hundreds will you find? If you find 80, you have 80% sensitivity because you missed 20. When you look at specificity, it's the other way around. If you have 100 non-infected patients, how many does the test mark as non-infected and how many as wrongly as infected? So if you have 100 healthy people or non-infected, if the test says, well, 5 have COVID, 95 don't have COVID, then you have a 95% specificity because you're right 95% of the time, but you said 5 people have COVID who don't have it. And so if you have
sensitivity is both how many false negatives and how many false positives you get using the test on a population.
Specificity tells you the false positives and sensitivity the false negatives.
Okay, got it.
And it's actually a very important metric. It sounds geeky, but it's important because if you look at only one of the metrics, I can invent a test for anything that is 100% sensitive if you don't look at specificity. It takes me 1 minute, right? Because you just give me people, I say everyone has cancer. Then I'm always right for everyone who has cancer. But I'm always wrong on everyone who doesn't have cancer. But I have 100% sensitivity. So that's,
there's a trade-off between these two when you're designing tests.
Right. You need both to be as high as possible. That tells you if a test is actually accurate. There is, of course, it always sounds much easier than it is. When you look in the details, it becomes very difficult. For example, there's clinical sensitivity and specificity, but then there's also technical sensitivity and specificity. Clinical means if you have COVID, if you're infected with COVID, do I find that or not? Technical means if I spike the COVID virus or whatever you're looking for into the sample, do I find it or not? So the technical sensitivity tells you, if you artificially create a sample that contains that stuff, do you find that stuff? That is, whereas the clinical sensitivity says, if you have the virus, does the test find the virus? That is a very important distinction, because if you have the virus, it does not mean that the sample contains the virus. Therefore, clinical sensitivity is much harder to achieve than technical sensitivity.
And I guess the way you establish whether your test will work is you have to go with technical sensitivity, because by definition, you just can't know for sure that you're going to have the virus in your sample in a clinical setting.
Exactly. You have many problems. So what the antigen tests, for example, do, I just give you the Abbott example. Abbott came out and says, our new test, the 5-minute $10 test, just came out yesterday, or has a 97% sensitivity, right? Which sounds pretty good. And of course, it cannot be true. So I saw it's like, okay, this is clearly not true. So then you look into like, okay, what did their PR department, why did they decide they can say that? And you look into the study. So what they did is they did a head-to-head comparison with a PCR test, right? So they said, okay, we test people who are positive on the PCR test and then give them that Abbott test too. So of course you have many questions that you get right away. So who are these people who are positive on a PCR test, and when did you give them the Abbott test? For example, if you take a PCR test and you're positive, and Abbott does that, Abbott probably needs 2 days or 3 days to figure that out, because they're not as fast as Quantgene. So you do a test, you wait 3 days, and you say, oh, you are positive. Let's do the Abbott test. That means you have 3 days for the virus to exponentially replicate, right? So in that, I'm not saying they did that, but I'm saying I don't know exactly how they did. They didn't describe that. But if that is the method, to first test a bunch of people, then pull out the positives and test them with your test, that's already not a fair head-to-head comparison, because you're testing, 100 times higher viral load potentially, because it's not the same point in time.
Gotcha.
The second thing is they only tested symptomatic patients, and they disclosed it. They said like, yeah, it's a head-to-head comparison with PCR on symptomatic patients. Okay, so that means they're all later stage. That excludes everyone who's not symptomatic, which is 35% of all COVID cases. And these are all little tricks where you make your test look pretty good. 97% sounds amazing. But you always have to ask a simple question in diagnostics. If you cut out all that stuff, can you guarantee me with your 97%, if I give you 100 people who are infected with COVID, you would find 97 of them? And then, of course, they would always say, well, it's not that simple, blah, blah, blah. And just my gut feeling on that number, on the 97% sensitivity, I think that translates with that study design and what they actually did. You were talking about 10, 15% of people you actually find. So that's a pretty big
difference. Not only that, if you're going to do, let's say, tens of millions of tests, now that lost 3% sensitivity translates to how many, false positives, right? A lot.
Yeah, but it is also not 3%. It's more like 80%. I'm pretty sure about that.
Well, even if it was, though, when you get to large numbers, every percent can make a huge difference in the number of people, right?
Yeah, you're absolutely right. Even if it would be 97, and I can guarantee you it is not 97% in real life. It is something much, much, much lower.
Yeah, just for listeners, 1% of 10 million is 100,000, so it's still a lot.
Exactly. So if you would test 10 million people who have COVID, you would tell 100,000 to go out in the population and that they are totally fine when they totally have COVID. So that's already not great. But I guarantee you, if they test 10 million COVID people, they will miss they will miss 5 million.
Okay.
And they also not, and the funny thing is, their stock goes up like crazy. I think some government person, I think White House or someone in the administration, bought $750 million worth of this test. There's not a single medical professional I talked to, or even anyone in a company who is in charge of sourcing these things that takes that in any way seriously. So I'm not like an extreme case of criticism. Everyone says, yeah, of course we're not buying these things. We understand antigen tests.
Oh, and the antigen test, not PCR. Got it. Okay. So back to PCR. Are you looking at the entire sequence of SARS-CoV-2? Or are you looking at just a conserved region of it when you do the PCR testing? Like, how does it work?
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
No, the PCR testing looks only at 2 regions in most cases of the virus. So the virus is a very specific RNA. So you don't need to look at the whole thing. You just need to see, is there any piece of the virus RNA in there that is unique to COVID-19? That's basically it. So it's a pretty straightforward test. What we saw at Quantgene is that the test is not the problem. They exist, they are highly accurate, and we did not have to invent the chemistry. We had to organize the sourcing, but then the most important thing is we had to apply a cloud system that connects these machines to the cloud and has an automated reporting system, which cuts out all these, very old school laboratory processes. And that gave us the edge why we are now America's fastest PCR turnaround on COVID. We can do same-day turnaround, and it's all about cloud systems and optimizing that workflow. It's not about the chemistry. The chemistry was already basically perfect.
Well, why would it take 2 days, 5 days, 7 days for other people? Why would it take so long if the chemistry works? What takes so long?
Well, we had to learn this the hard way when we started and actually went to the lab. Imagine you're a lab, right? A lab just means there is a guy who sits on a desk in front of a PCR machine with a pipette, and he gets 2 samples in, and he puts a little buffer on these samples and pipettes it back and up and back, and then puts it onto an Eppendorf plate, runs it for 50 minutes, and then gets the results. Okay. And there's a courier that drops off these samples. So you get 2 samples in, you do it, it's all fine. You have the results after, 3 hours. And then you write down these results, you look at it and say, okay, this was Richard, this was Joe, both are not detected. You type it into your system, you print it out, and you send them an email, right? No problem. That's how labs actually work. Now, what happens if you drop 20 of these samples? Okay, then you have to do this 20 times. What if you drop 20,000 of these samples? You will literally scale the time in a linear way if you do it this way. As long as you have any manual labor involved in the reporting or accession of these samples, you are completely screwed if you scale from 1 sample to 10,000.
I see.
And so it's literally the dumbest problem. It was a problem that the labs literally had 1 full-time administrator who dealt with their samples. And normally they can do 10 samples a day. If they do 20 samples, they need another administrator. If they need 10,000 samples, they need to hire 1,000 administrators. And that is exactly what happened at LabCorp and Quest. And of course, they didn't hire 1,000. They just said, oh, you have to wait 5 months.
So what about the array itself that you put the samples in? I mean, what about the machines? I would think there'd be bottlenecks. No one would have, let's say, enough, arrays, microarrays to put all these samples in. No one would have enough machines to run it in parallel. What about that part of it?
It's all part of the problem, and it's the problem where everyone focuses on. But when you do a level-headed analysis, and that's what we are good at, we go in, take a step back, look at the entire process, and identify the bottlenecks, and identify where are the efficiencies here for the system. The actual machines that's the smallest bottleneck, the actual machine. It's still a bottleneck, but it's the smallest of all. Trained lab technicians are the second smallest bottleneck. By far, the biggest bottleneck is workflow. To just look at the thing and optimize the workflow, which is a pure software problem. You have to basically turn everything into a digital workflow. You have to automate all the reports and the numbers. And then you have to build both the process and you have to build the software tightly into the process, and you have to change the process so it is harmonized with the software. And that's, of course, not something labs normally do.
So is what you're doing a bolt-on to an existing lab, or do you have your own independent lab and these cloud systems?
Well, so that's also an interesting question. The way we design things at Quantgene is we first design the system in theory, right? The blueprint for the system, say this is the perfect system. Then we develop the cloud systems, and then we plug in the components, the actually brick and mortar components, or the machines or chemistry. How we plug them in is tactical, right? Because we don't care. In the end, we need the system to be perfect. In some cases, we use our own labs here at our headquarters. In other cases, this is a regional play because you need, in order to have the same day turnaround, you need to have a local lab. So if you do it in Atlanta, you cannot have a lab in California. So then we need more labs, and we are looking into acquiring labs, into starting new labs, and into partnering with existing labs, and we do all of the above. That's a tactical decision. Do we find a good lab that is willing to partner at reasonable prices, that is disciplined and can be quickly trained on the software? Then we do that. Or is this a state where you can quickly get a clear license? Then we do that ourselves, depending on the personnel and everything. So, all these things for us are unimportant. You have to get to your blueprint and make it work so you can deliver same-day turnaround times to the patients. The same is true for if we partner with a lab. What is what conditions does this lab have to meet? And the answer is nothing other than having a clear license, because we can install the entire equipment and we can source the assays with our partners very quickly. So we have PCR machines, we can put them in, we have the assays to put them in. So it's literally just we need bodies who are trained, and we need clear licenses locally. And then we can do this very quickly.
Do you have different levels? So does a lab need to process a minimum of, at peak times, 100 samples a day or 1,000 samples a day for it to be worth it?
Yes, to start a new lab and in your region, we are looking at like 2,000 samples a month. And that's kind of the critical mass to justify that.
Okay. And then the data itself, if you work with a lab in some state and you help them do this, does the data go onto like your systems networks, and are you able to, pseudonymize it and query it for research, or does it have to stay with the lab that you're partnering with, and you help them collect it and put it in the cloud, but it stays with their system and you don't have access to it?
It's always on our cloud system, but it's a HIPAA compliant, CLIA compliant cloud system, and technically the laboratories license the software. That's like the legal situation. So it's their software, but we are the software provider. And so they can download that, and mostly they store it locally on top of our cloud system for clear compliance reasons. But they own the data. Well, the patient owns the data, the ordering physician owns the data or has access to the data, and the laboratory has access to the data. And there's reporting requirements to the states and federal government.
Okay, got it. What about the PCR test? Is it just a pass-fail, or is there a ramp rate of multiplication of the sample? I mean, what parameters of the PCR test provided any nuance, or does no one care? It's either positive or not positive.
Well, unfortunately, most lab directors don't care, but that's also why you see problems, right? So the way it works is you basically have a two-dimensional graph. One shows you the frequency of the laser that's being reflected from the probe, and the other, on the x-axis, you have the cycles. And each cycle is called an amplification cycle. So each cycle doubles the amount of genomic material in the sample. And all that happens per well. So you have an Eppendorf plate, you have 96 wells on that plate, and in each well, you have one sample. And there are two probes in each well. One is the control probe that just looks at basically a random control piece of DNA just to make sure something is in there. And the other looks for the virus, RNA. And what is then being plotted is basically just a curve that says per cycle, how much fluorescent light do I get back per piece. And the way it works is there's basically a probe in there that finds your target genomic sequence. And if it exists, it just gets multiplied. And every time it gets multiplied, a fluorescent marker is being released. And the more you multiply, the more is released. And that means you get an exponential curve if something is there, because you double it with every cycle, right? And that ends up being two curves. One is the control curve that tells you, is there anything in the sample? Like, is there any DNA in the sample? If not, the sample is broken. And the other curve tells you, is there COVID-19 in the sample? And so if you get one curve, that means it's not detected. If you get two curves, it means it's detected. If you get no curve, it means it's invalid and you have to rerun it. So you need oversight over these results and you have to make these decisions. They can be automated to some extent, but there is also, the problem is how do you read out these curves with the computer, right? So for example, if you have a threshold on the y-axis and you just test if that threshold was ever broken through, there are certain error curves in a PCR where it's not an exponential curve, but it's a curve that goes first up and then down, which is just an error. This cannot happen. But if you just measure the threshold breakthrough, then you would say, oh, it's positive because we saw that curve. But then you look at the curve and say, no, that's a broken curve. So there's a qualitative aspect to it. So you have to control your positives and check that they're actually true. But
what about extrapolating backwards? Once, if you get, if you see there's COVID there and you do get an exponential, why not extrapolate backwards to estimate how much virus was in the sample when you sampled it? Because that might tell you how far along the person is in terms of viral load, or maybe at least just tell you their current viral load at that moment.
That's a good idea, but that doesn't work because you don't have a good reference point. Yeah, you don't have a benchmark. What if you took it can easily be if you have two patients that you take 10 times the amount of sample from one patient without knowing it, because there's no way to control, there's no quantification on that.
But if you're doing, let's say, nasal swabs on 100,000 people or 1 million people, if you kept all the data, you could see on average, the sample size is going to vary a little bit, sure. But you could see, you could look back and say, of the asymptomatic people, their viral loads tended to appear to be, a lot lower than the symptomatic ones. I mean, I would think you could get some very useful data from that.
Yeah, I would doubt that a little bit because there are too many. It's too imprecise, the whole system, to do that. Because this amplification, if you have one cycle delayed for whatever reason in the chemistry, so it's I think it's a good idea, but I would say, just based on my experience with molecular diagnostics, I wouldn't rely on this data. I think it's too far away from the truth. There are too many error sources to really throw this off. I think if anything, you look at other metadata that are interesting, that are more on a population level. I think then it's becoming interesting if you have a lot of data of patients and you repeatedly test these patients, who actually gets sick, how does this relate to other people? I think COVID is less of a deep molecular diagnostics data problem and more of a Palantir problem, like a population problem, like rates over time, who gets it, who else gets it, when do people get it, where do people get it? I think that's the big, interesting question.
Well, but again, if getting it means I'm asymptomatic and nothing bothers me, who cares? If getting it means I die, well, yeah, I care a lot more. So I don't know. I just think that this should be an area. I know you can't do everything, but I would think there could be things learned from this, especially if you're going to do 10 million of anything. There could be a lot of juicy details in there.
There's definitely a lot of juicy details in there. Yeah, I believe that. But right now, the urgent need is that people simply cannot get tested and that the turnaround times are terrible or the tests are bad. So I think we are really focusing on more like an infrastructure play here and say, if you need the highest quality COVID test and you need it same day and you need it at scale, we do it.
Yeah, and if you wouldn't mind, can we go back into the test itself and go into a few more details of how the test works?
Sure.
Because I hear PCR testing, I'm sure everyone else hears it, but the real nitty-gritty of actually how it works. So you were saying that you'll pick, 2 regions of the RNA that's unique to COVID, and you'll attempt to amplify both, or what, literally step by step, how does the test work, if you don't mind?
So you want a control, and you always, in a PCR test, you always want one curve or one marker for what you are looking for and one marker for some type of control. And the control is important to tell you if there's anything in the sample. And so normally what you do is you're taking a random piece of DNA segment that you pick as a control. So you tell, okay, is there any material in the sample? So it's not the virus. You don't want the control should not be from the virus. It should be from your DNA or something else.
Okay. So what the controls, they're not patient specific. You just pick a reference strand of RNA to compare. Is that what it's used?
Exactly. So we all have a DNA, and we have many regions of our DNA need to be identical where no one has any variants on there. And you're taking one of these and you say, well, that needs to be in the sample. If that is not in the sample, there's no material from a human in the sample. And that
Okay,
means
so you get your reference. Okay. And then literally, how does the amplification happen? What happens?
So the PCR technology is one of the most fascinating things is one of the base technologies in molecular diagnostics. And so polymerase is an enzyme. And this enzyme has a specific task. And the task is to take single-stranded DNA. So you have double-stranded DNA, the helix. So we have two strands of DNA that are attached to each other. And what polymerase does, it takes a single strand of DNA. So once you separate that, you have single strand, and complements that strand. So it basically builds you the complementary strand, right? So imagine you have a ladder and you rip it apart and you have these two pieces of the ladder. The polymerase is a protein that attaches to this single-stranded ladder and just adds the other part to it. And so what it basically does is it looks like if you have a T, it adds a G, an A, and if it's a C, it adds a G, and so on the other side. And so the PCR technology, what it basically does is it heats the sample up to 96 degrees, which leads to a separation of the DNA into single strands. And then it cools it down slowly. And when you cool it down, at some point, the polymerase can jump into action. And then the polymerase says, oh, look, there are all these single strands, so I can complete them now. Now, the trick is that there's something called the annealing temperature, which means if you have heated up the sample to 96 degrees and you have separated the DNA, at what point does it anneal again? At what point do these two pieces automatically attach to each other again? And there's a certain temperature that is a function of the length of these fragments. The shorter the fragments, the faster they anneal. And so what people invented is they said, well, I can inject into that sample a piece or a sequence of DNA that is complementary to a region on the DNA that I find interesting. And if that happens, this little piece of DNA anneals faster than the other part of the ladder because the other part is much longer. And so it anneals faster at a higher temperature. So you throw all these little pieces in there and the temperature is 96 degrees. You cool it down, and at 70 degrees, let's say, this little piece now anneals to the specific part where it fits on, and then you stop cooling it down. So the rest doesn't anneal. And then the polymerase sees that, and the way polymerase works, it doesn't just complement a single strand. It only complements a single strand if it's double-stranded at some point. So if everything is single-stranded, polymerase doesn't do anything. If polymerase sees, oh, it's double-stranded, but here it starts to be single-stranded, then it complements it. And so what it does allow you to do is you can basically create a primer, like a little piece of DNA, cool it down to a certain degree, and then the polymerase amplifies or copies that piece of DNA, but only that piece of DNA. And if you do that, you create a copy of only one piece of DNA that has your specific primer sitting on it. And then you heat it up again, and they cool it down again, and then you do it again, because then everything gets separated again, and then the little pieces anneal again, and then you make another copy. But now you have 4 copies because you created 2 before. And so that's an ingenious process that allows you to take any type of RNA or DNA and start making copies in a targeted way, where you only copy something that looks exactly the way you want it to look like. And if that piece you put in there doesn't exist, nothing gets copied. But if it exists, if it's a virus sequence, then it gets copied. And the key here is that you can make single molecules visible, which is completely impossible normally. You can never see a single molecule. You can't even see 1,000 or 1,000,000 viruses. They're too small. But if you turn them into 200 billion ones, then you can see them.
Well, when you're taking a sample from, like a nasal swab, let's say, there's going to be all kinds of human DNA. There's going to be viral DNA from various viruses. There's going to be all kinds of stuff in that sample. So the part of SARS-CoV-2 that was picked to amplify is so unique. And can you can tune the polymerase to only amplify that, or does it amplify everything, and somehow you're able to pick out that signal the particular RNA that you want to see if it's there that's been amplified?
Yeah, the key is you need this, what's called a primer. And this primer is simply a sequence of your target, right? And so, yeah, the sequence, if it's not unique, you will amplify all kinds of stuff. You need a unique sequence. So you can only amplify something in a targeted way if you have a unique sequence. But that's not very hard, right? Because every living thing with a DNA, or a virus are not living, but everything with a DNA or RNA, you can identify a unique sequence, right? So the COVID-19 virus has, of course, unique elements to it that no other virus has. Otherwise, it would be the same virus.
But who picked the elements? I mean, I know that viruses mutate. This one's an RNA virus. It mutates. It may not mutate crazily, but how do you know the region that you're picking is the right one, that it is truly unique, that there's not other viruses out there that are common that have this sequence, to give false positives, and again, that it won't mutate away where it's not useful?
Yeah, that's a very good question. So when a new virus occurs, you need to sequence the virus. They did this very quickly. That's not very hard to do. And then you see the virus sequence, and then you upload it and compare against all other virus sequences that we know of. And then you can just see where's a unique region. That's the step one of developing these things. That's not rocket science. You just sequence the virus, you upload it, compare to all the other viruses, and ask the computer, is there any region that's totally unique? Yes, there are tons of regions. Okay, here are the regions. Okay, you can develop primers. And the next thing is a biological understanding of the virus. How does it mutate? And viruses mutate in very different ways. So some viruses, because the mutations with viruses are not random, they are actually very targeted. So some viruses mutate in a way where they have segments on their RNA and they interchange the segments. It's just like building blocks. The building block itself never mutates, but the sequence of the building blocks constantly gets changed by the virus. That's one type of mutation. Other viruses have regions that are very stable and regions where they constantly mutate in random ways. So these viruses are very mean. They know exactly what they're doing, kind of. But they cannot randomly mutate, then they would never exist, where they would just constantly not cease to exist. So they need to mutate in very specific ways. So you find your unique sequences, and then you find out which part, are these sequences in parts that mutate or not mutate? And then you try to find the ones that don't mutate, and then you have a more sustainable detection. It's not super simple, but it's like roughly, you get the idea.
Well, how many unique sequences of SARS-CoV-2 are used in PCR? Is it just one? Is it multiple uniques? And does it make it better if you have more unique, stacked on top of each other with multiple primers?
It depends on the PCR test, but I think ours uses 2. I can't even tell you the exact number. I think it's 2 regions that it looks for.
Okay. That's better than 1, but yeah, 2 is good.
Yeah, but you don't want to have too many. That it creates more false positives at some point, right? If you have too many, then it might look, if you have any of these, then you have a positive. So at some point you run into a higher probability that you just randomly have another virus that looks like that.
Right, that's true. Yeah. And I guess if you have more than one, you could look at the prevalence of, the 2 compared to each other as well. It should have about the same prevalence. If one starts to amplify a lot and the other one doesn't, something strange is going on.
Well, but that you can't tell, because they have the same fluorescent marker, because normally you only have 2 colors, one control and one virus. So if you have 2 in there, you give them the same color, so you don't know.
Oh, okay. I didn't know they couldn't tell them apart. Okay.
You can do sequencing, but that's much more complicated and expensive.
So getting back to the rollout of the testing now, what is the current need, let's say in the United States, of tests per day or per month, and are there efforts ramping towards this? Like, what do you think is going to play out over the next 6 months in terms of your testing getting out there and being used? Well,
I think, for us, it's really, we are growing pretty fast, but we have a tiny little share of the market, obviously, because we just started this. The need is crazy. It's like enormous. And for a company like ours, it's more like getting the word out that we even exist. Because I think there are false narratives out there saying, PCR tests don't work, they take too long, so they are not even an option. That's what most people think at this point. Like movie productions and other urgent, people who need this urgent result. So we see, for example, movie productions, they're all deciding to leave the United States right now, which is an enormous cost to everyone. because they think it's not. Yeah, I mean, we hear this with every movie production company that's large is considering leaving Canada, New Zealand, Australia. And you can imagine the costs for that. And, we need to get the word out quickly to them. Like, guys, we are already testing at scale in LA, same day turnaround. That would solve the entire problem of the industry. So it's kind of funny that the only problem we have is to tell people, which sounds trivial. It's not very trivial. There's just a lot of noise out there. We need to ramp up PR. We have to tell people, no, it's just, we can't do that. We can't do it at same day turnaround time. But everything is moving at lightning speed, right? If you miss out on telling everyone that fast enough, they might just all leave in the movie setting. And we see these very desperate moves with antigen tests, which is just a bad idea. There are certain contexts where they might make sense, but they fundamentally don't make too much sense because if we can't rely on them, what's the exact point? And so, for us, it's mostly getting the word out and telling people, because it's not how laboratory people think. They think what we are doing is utterly impossible because they're not cloud systems people. Cloud systems people, they would say, well, we did this in logistics and we did it, in all kinds of places. Of course, it's possible to streamline a process and make it cloud compatible. But in a lab, it has never been done to this extent. And so it's kind of a very funny, weird situation we are in, that, we just have to tell people and they have to wrap their head around that this is an option now and look at the costs and make a decision.
Well, too bad you can't amplify knowledge of quantity as fast as you can amplify RNA.
That would be very nice, yeah. So that's good why I'm also talking to you right now about these things. I think we just have to get the word out. And and when I see all the things that are happening in COVID are just so breathtakingly stupid, some of them. Like, these decisions are wrong, why do you go for antigen tests? I think it's a lot of politicians who I don't even want to blame, but they want a solution. It sounds so nice for them. It's like, oh yeah, maybe now we can test everyone. But it's low resolution thinking. And of course, the medical professions are not agreeing.
Do you think there's, it seems like in certain areas they want to test people every day or every few days. Do you think that's a good idea or bad, or why?
It all depends, what we are talking about. If you have a movie set where you hang out in close vicinity to each other every day, you should test 3 times a week. If you have a manufacturing facility where people have to be in close contact and cannot socially distance, you should probably test 3 times a week. If you socially distance or don't even have to go to the office, then you don't need to get tested as much. So it's all a risk assessment, depending on the context. But every time you want to have dense crowds, I definitely would recommend to get everyone tested, because it's a little reckless to not test them.
So if this was fast enough, that would allow, a negative test being a requirement for entry to work or to an event or those kinds of things, or a country.
Exactly. We have also some travel requirements where you need to show a test that within 72 hours, that was done within 72 hours. So you can imagine it needs to be done within 72 hours, but you also need the results. If you need 48 hours for the results, you have basically 24 hours to travel, and then you're screwed. So you need same-day results in order to make many of these things work.
Okay, makes sense. Well,
also,
Joe,
imagine you test someone and they are positive, and you get the results back 3 days later, and in these 3 days he's just running around. That's just not very smart.
No, that's true. Yeah. Well, Joe, I'm glad you came back. Like you said, you're very innovative. I love having you as a guest. It's great. So I'm going to get the word out about this for you by getting this podcast out there. What do you want people to know that are listening? If they, obviously it sounds like the movie business would be great. What other kinds of organizations or companies or people that listen to this should contact Quantgene and find out about working with you?
Well, anyone who is looking for COVID PCR, so high accuracy solutions that are very fast turnaround, that can be governments, of course, it can be hardware and can be manufacturing. We have logistics companies, movie, of course. I think there are many others too, retail organizations, events. The NFL is a big topic where we know that they're considering canceling the season, all kinds of things. College football. So I think, whoever is exposed to any kind of discussion It's just would be great to get the word out that we can now deliver same day PCR COVID results to nearly 100% accuracy.
Okay, very good. So Joe Bhakdi, head of Quantgene, thanks for coming back on the podcast. I appreciate it.
Awesome. Thanks a lot. I really always a pleasure to be on your podcast, Richard, and thanks for doing that.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.